So, if your reduced form is this, what does that tell you about the two lines? This is a reduced matrix for two linear equations, okay? So what's this mean about the lines on your graph?
Zero equals 2.
Sorry?
0 equals 2 in that one line.
What about 0, 0, 2?
Are they parallel?
For the equation, meaning that there'd be no solutions.
Well,
0 equals 2.
it means there's no solution, but what's that tell you about the two lines?
They don't intersect, they're parallel.
Okay, so this means that the lines are parallel. But they don't intersect. Okay? What's this mean?
Equations are on top of each other.
Yeah, they're the same line. Okay? So you might think about what this could mean. First of all, in terms of simultaneous equations, what could that represent?
Three equations?
Three equations, three unknowns, right? Three linear equations, three unknowns. So what can you tell me about the graph of an equation in three unknowns?
3 dimensions.
It's going to be a plane.
It's going to be a plane. So now what can you tell me about the planes?
They're on top of each other.
Again?
Are they on the same plane?
The what?
Are they on the same plane?
All three of them? He said, are they in the same plane? I'll say no, because that implicitly means all three of them are in the same plane.
2 of them intersect. One is parallel. Well, one is the same.
Two
as the
of them are
other.
in the same plane, but one of them, one of them is not in the same plane as the other two. If it was all three in the same plane, they would all reduce to zero. Okay? What about
Planes are parallel to each other.
yeah, two of the planes are parallel, okay, but they don't intersect. That kind of makes sense by analogy, okay? Okay. So this will correspond to three equations, three unknowns. This would mean that the three equations give you three planes, because any equation and three unknowns is going to give you a plane. Haven't proven that, but you see that later on. And maybe in this course too. But okay, you got three planes. Two identical. And one is different, okay? Here you got three planes. Two are parallel but not intersecting, okay? And one's not parallel to the others. And when I said here one different, I should have said one not parallel to the others. It could be different, but still parallel. So I was a little careless with my wording. Okay? Well, if two planes intersect, or in this case, this plane would intersect the other two, which happen to be identical. And what do you get when a plane intersects another plane?
Line.
You get a line, right? Okay. And what do you get over here?
Two lines.
Get one?
Two lines.
Two lines. Because this plane that's not parallel to the two that are parallel, but not the same, will then intersect this one on a line, intersect this one on a line. Okay? So that geometrical interpretation is important and significant, and when we talk about linear transformations and how dimensions work and stuff like that, you get it. So, okay, well, pretty good intuition. How about this? First of all, what would that represent in the context that we're talking about here? Be four equations and four unknowns, right? How's your intuition with visualizing four-dimensional space? Well, if you're like everybody else in the universe, it sucks. Okay? So four equations. Okay, so what you have is four hyperplanes.
There be two parallel three-dimensional spaces there.
Yeah, two of them would be parallel but not intersecting. But there are also two of them that intersect. That are the same, right?
Is that a -1? Out of curiosity.
Two are parallel, don't intersect, two of them are identical.
Is that a -1 under the 5 or
Huh?
under the 5?
I'm sorry, there's a lot of noise across the hall and I don't have my hearing aids in.
Under the 5, is that a -1?
Yeah,
Okay.
doesn't matter what it is, it's not 0. Whatever it is. Okay? So, go back to this one. What's the dimension of a line? Line's one-dimensional. Okay, points are 0-dimensional.
So
Planes are
for-
2-dimensional.
For hyperplanes,
Space is
wherever
3-dimensional.
they,
I'm sorry?
so for these, wherever they intersect, you'd have a full plane.
Where they intersect?
Well,
Which one are you talking about?
The one with the 4 unknowns, if they intersect,
Okay, we'll get
you'd
to
have
that
full
in a
plane.
minute, but you might have made a good jump there. Okay? But let's talk about dimension then. Okay? So first of all, a line has dimension 1, plane has dimension 2, space has dimension 3, you know, it's the space we live in. In higher dimensions, well, that'd be 4-dimensional space. Okay? So, now these lines are in 2-dimensional space. They live in 2-dimensional space, right? So, two lines in 2-dimensional space, if they don't have the same slope, they intersect where? At a point. What's the dimension of a point?
0.
0. If they're identical, then they intersect in a 1-dimensional line. Okay? So, two lines in 2 dimensions have a 1-dimensional intersection, right? Now, if we have this, what's that tell us?
Intersect at one point.
Yeah, this tells us the lines intersect at the column vector 3, 5. Semicolon tells us that's a column vector, right? And yeah, y'all did fine with that notation. So this is a 0-dimensional intersection. Okay? Okay, well, now you got 3 equations and 3 unknowns. What happens here? Well, you get a 1-dimensional intersection. Your intersection is a plane, right? In this case, these 3 planes do not have a common intersection, right? Now I should say no common intersection. Okay? Now, of course, if you had a 1 and a -2 here, that would tell you your intersection is a point. Okay? So, let's just write that case down. And of course, if you had a 1 here, you wouldn't have the 4 here. Not if you do the complete reduction. So this would be common point 3, -2, 5, zero-dimensional intersection. Okay? I'll leave you to think a little bit about this. Okay. Well, yeah, go ahead and think about it. What do you think? Because you wanted to say something about it.
If two of those are identical, they be a full three-dimensional space where they intersect.
All of three-dimensional space could be a hyperplane within four-dimensional space. Matter of fact, you could have 4 independent three-dimensional spaces within a four-dimensional space. Okay? So each equation would represent a three-dimensional space within 4 dimensions. Okay? So we can expand that since you bring this up. Each hyperplane is three-dimensional. Okay? So, just comments off to the side. Each equation represents a three-dimensional hyperplane. In four-dimensional space. Don't even try to visualize it, but you can think about it. If you understand two-dimensional, three-dimensional space, you can use that as a basis for thinking about higher dimensions. And we don't stop at 4, we go up to any number of dimensions. Okay? And some of your hyperplanes might be of higher dimension than others even. It gets complicated, but fortunately in linear algebra, you don't have to do that much visualization, but it helps you understand dimension and stuff that's very important. Okay. So you got 4 hyperplanes. Okay? 4 three-dimensional spaces within a four-dimensional space. What can you say about them?
Can you repeat that?
Okay, yeah, sure. It's a mouthful. You've got 4 three-dimensional hyperplanes in a four-dimensional space. So what can you say about the way those hyperplanes are related? Or based on this. For example, if 2 of them are identical, it means you've really only got now 3 independent hyperplanes. Okay? Now, if two are parallel but not intersecting, whatever parallel means, well, what would that mean? If planes are parallel and not intersecting, what can you say about their intersection? Empty. There is no intersection. Intersection's an empty set. Okay? Well, so what are you going to say about two parallel but not intersecting three-dimensional hyperplanes? Well, it means they don't intersect. It means they don't have any points in common. Right? Okay, so we can say we have four hyperplanes. But now we get down here and we can say and independent might not be a good word to use. It might be a little misleading. I'm going to say it anyway. Okay? Two are parallel, but they don't intersect. So, well, that's what implies, well, okay, this implies this. This implies, well, nothing in common between those two. So actually, only three independent comes from this, as I was going to say. But then two of them are identical. If they're identical, they intersect. So there's another one that's not independent. Okay? So from this, there are now only two that are independent. Okay? Okay, so now two of them are independent, but they will have an intersection. Okay? Independent doesn't mean they don't intersect. If they don't intersect, they are independent. And if they're identical, of course, they're not independent. Okay? So you can draw these kind of conclusions. Well, I'm going to introduce a little terminology that will make more sense of later. I'm going to say that this one has a rank of 2. And this one has a rank of 3. Okay? And this one has a rank of 1. Okay? And this one has a rank of 2. Okay? We don't talk about the rank for this one or this one because they're not intersecting. They don't have solutions. Okay? And this one, same thing. Okay? So I'm just kind of introducing that terminology, and it's really this number of independent rows. That's what the rank is. Okay. whatever the matrix was, the rows were independent. If they were dependent, you'd end up with row zeros, okay? Here, you got a row of zeros, meaning that the two equations were not independent. Okay? And so forth. Okay? Just a little terminology and a little geometric reasoning. Fair enough? And that kind of takes off on what I asked you to do for this, for last time. Okay? When you're reducing the matrices, when I ask you to say what this means, what this matrix means about the lines, hopefully you said, oh, you knew when they were intersecting, you knew when they were parallel, but not intersecting, you knew when they were parallel but right top of each other. I think you did. And it looked totally, but I saw you commenting on it on at least one or two problems. And you seem to understand it because you answered everything. Okay? So I think you're good with that. Just saying that that whole idea extends from 2 dimensions up to higher dimensions. So one of my purposes of just showing how you go from 2 to 3 to higher dimension. Okay? And how the reasoning is really kind of the same, but it's harder to visualize at each step. Impossible to visualize when you go beyond 3, but you can still say a lot. Okay? I know what a 3-dimensional hyperplane in a 4-dimensional space means. Yeah, well, you got to work out some mathematics, get some results, and then get a feel for it. Okay? And you'll never be able to visualize it. You can project it and you can visualize how it looks if you shine a light on it from this hyper direction or whatever. Okay? And that's kind of interesting. But that is what it is. That's based on what you did for homework for Tuesday.